70,000 years ago, a star came within touching distance of our solar system. Not metaphorically, not within a few light years, the comfortable astronomical definition of nearby that still means trillions of kilometers of empty space. Within touching distance in the only sense that matters for a solar system, close enough to reach inside the Oort Cloud, the vast shell of comets and ice that marks the outer boundary of everything gravitationally bound to our sun. Close enough to pull things loose. The star is called Scholz's star. It is a dim red dwarf, currently sitting about 20 light-years away, invisible to the naked eye, unremarkable in every catalog it appears in. Nobody knew it had done this until 2015, when two astronomers at the University of Rochester ran its trajectory backward through time using proper motion data and found something that made them check their calculations twice. 70,000 years ago, Scholz's star was not 20 light-years away. It was 0.82 light-years away. Some estimates put the closest approach even tighter, as close as 0.6 light-years. Inside the outer boundary of the Oort Cloud, inside the gravitational neighborhood of our sun in the most consequential possible sense. A star passed through our solar system while human beings were alive to not notice it, and we are only now beginning to understand what it left behind. First, let's establish the scale of what actually happened. 0.82 light-years sounds like a large number. In human terms, it is incomprehensible, approximately 7.5 trillion kilometers, a distance that light takes 10 months to cross, a distance that would take a spacecraft launched today more than 15,000 years to traverse at Voyager's current speed. But in astronomical terms, in the terms that govern how stars interact with each other and with the planetary systems around them, it is extraordinarily close. The average distance between stars in our region of the Milky Way is approximately 4 to 5 light-years. Stars are typically separated by distances that make gravitational interaction between them negligible. At 4 light-years, two stars barely notice each other gravitationally. Their mutual influence is real but vanishingly small. At 0.82 light-years, the situation is different. At that distance, Scholz's star was well inside the Oort Cloud, the spherical shell of comets and frozen objects extending from roughly 0.8 to 3.2 light-years from the Sun. The outer Oort Cloud begins at approximately the distance of Scholz's closest approach, which means the star did not pass near the Oort Cloud, it passed through it. Scholz's star is not alone. It has a companion, a brown dwarf, a failed star that never accumulated enough mass to sustain nuclear fusion, orbiting Scholz's star at close range. The system that passed through our Oort Cloud 70,000 years ago was not a single object, but a gravitationally bound pair. A dim red dwarf and its dark, cold companion, moving together through the outer reaches of our solar system on a trajectory that brought them closer to the Sun than any star we have confirmed in the observable history of our solar system. A brown dwarf is not a planet and not a star. It is something in between, typically between 13 and 80 times the mass of Jupiter, warm enough to glow faintly in infrared, cold enough that hydrogen fusion never ignites. Scholz's companion is approximately 65 times the mass of Jupiter, massive enough to exert its own gravitational influence on the Oort Cloud objects it passed through, a second gravitational source moving in tandem with the first. Two objects, one event, both of them pulling on a trillion loosely held icy bodies as they transited the outer solar system. Here is what that transit would have looked like from Earth. 70,000 years ago, modern humans had already migrated out of Africa. Populations existed in what is now the Middle East, possibly in South Asia. The species that would eventually build telescopes and write equations was already present, anatomically modern, cognitively capable, looking up at a sky that was, in one significant way, different from the sky we know. Lower. Scholz's star, at closest approach, was not invisible. It was dim, very dim. At its closest, it would have been at the edge of naked eye visibility, magnitude 11.4 under ideal conditions, which means it would have been invisible to most observers without exceptional dark skies and exceptional eyesight. But it was there, a faint reddish point among the stars of the constellation Monoceros, moving measurably night after night against the fixed background stars. Moving because at 0.82 light-years, the star's proper motion, its apparent drift across the sky, would have been detectable over years. No human being who saw it knew what it was. No tradition recorded it. No cave painting preserves its passage. It was simply a faint star, slightly redder than its neighbors, drifting almost imperceptibly against the background of the night sky, while beneath the threshold of any perception, it dragged gravitationally through a trillion objects that had been sitting undisturbed for billions of years. And then it moved on. The discovery of Scholz's close approach was made by Erich Mamajek and Scott Hillenbrand in 2015. Their method was elegant and indirect. Scholz's star has an unusually low proper motion across the sky for a star so close to us. Nearby stars generally appear to move quickly across the sky because we are watching them from close range, the same effect that makes nearby objects appear to move faster than distant ones when you look out a car window. A nearby star with low proper motion is not actually moving slowly, it is moving almost directly towards us or directly away from us, which means its motion is primarily along our line of sight rather than perpendicular to it. The component of its velocity we see as sideways drift is small, not because it is slow, but because it is pointed nearly at us. Mamajek and Hillenbrand measured the radial velocity of Scholz's star, its speed along our line of sight, and found it was moving away from us roughly 80 kilometers per second. Running the trajectory backward through time, accounting for the gravitational influences of the Milky Way and neighboring stars, they found the closest approach. 70,000 years ago, 0.82 light-years. A calculation performed in a university office using velocity measurements and orbital mechanics, revealing a cosmic event that happened before written language existed. Now, here is the question that keeps planetary scientists occupied. Scholz's star did not collide with anything. No comet impacted another comet. No cataclysmic energy release marked its passage. It simply passed through, its gravity reaching into the population of loosely bound icy objects and tugging selectively at the ones whose orbits brought them close enough to feel the difference. The objects most vulnerable to perturbation are the ones on the outer edge of the Oort Cloud, the ones already barely held by the sun's gravity, whose orbits are already nearly parabolic, already nearly unbound. For these objects, a gravitational nudge from a passing star is the difference between an orbit that returns to the inner solar system and an orbit that escapes the solar system entirely.
Or the reverse. A gravitational perturbation can send an Oort cloud object inward just as easily as it sends one outward. Objects nudged onto trajectories that bring them toward the inner solar system begin a journey that takes between 1 and several million years to complete, falling slowly inward from the outer edge of the Oort cloud toward the sun, their trajectories slowly bending under the sun's increasing gravity, eventually crossing the orbits of the outer planets and sometimes the inner ones. Scholz's star perturbed the Oort cloud 70,000 years ago. The comets it disturbed are still falling inward. In 2018, a team of astronomers led by Carlos de la Fuente Marcos at the Complutense University of Madrid published a study examining the trajectories of known hyperbolic objects in the solar system, comets and other bodies whose orbits are so elongated they appear to come from interstellar space or from the very outer edge of the Oort cloud. They found a statistically significant clustering. Among the known hyperbolic objects, a disproportionate number had trajectories that, when traced backward, pointed toward a specific region of sky, a region consistent with the direction from which Scholz's star approached 70,000 years ago. Not all of them.
The signal is statistical, not definitive, but the clustering is real enough that the authors concluded Scholz's star's passage is the most likely explanation for the anomalous concentration of trajectories. These are the objects that Scholz's star disturbed. Some of them were rejected from the solar system entirely, sent on hyperbolic trajectories that will carry them into interstellar space, joining the population of rogue objects drifting between the stars. Others were sent inward. Some of those inward falling objects have already arrived in the inner solar system and been observed. Some are still falling. Some will not arrive for hundreds of thousands of years. We may have already seen Scholz's star's influence crossing our sky as a long-period comet without knowing what sent it. But here is the part of this story that is hardest to sit with. We found Scholz's star because of its current proximity, 20 light-years away, and its measurable velocity. We could run the trajectory backward because we have precise measurements of where it is and how fast it is moving. What we cannot do is run every star's trajectory backward with the same precision. Gaia, the European Space Agency's stellar mapping satellite, has measured the positions and velocities of nearly 2 billion stars. For a fraction of those stars, the ones close enough and bright enough to have high-quality measurements, we can calculate close approaches with reasonable confidence over the next several million years. But Gaia's catalog is not complete. The galaxy contains 200 billion stars. Many of them are dim, distant, and moving in ways that make precise velocity measurements difficult. Brown dwarfs, like Scholz's companion, are particularly hard to detect and catalog at large distances because they are so faint. Scholz's star itself was not known as a nearby star until relatively recently. Its companion brown dwarf was only identified because of its proximity. At 20 light-years, it is close enough to detect. At 200 light-years, the same system would likely be uncatalogued. The question this generates is not comfortable. How many other stars have passed through the Oort Cloud that we do not know about? The geological record offers a partial answer, and it is ambiguous in the way that all deep-time evidence is ambiguous. There are periods in Earth's history, the late heavy bombardment around 4 billion years ago, the end Ordovician extinction around 445 million years ago, various other impact-associated events where the rate of large impacts on Earth appears to have increased. Some researchers have proposed that periodic comet showers triggered by stellar close approaches or by the oscillation of our solar system through the plane of the Milky Way are responsible for these pulses. The evidence is contested. Identifying a comet shower in the geological record requires distinguishing it from the ordinary background rate of impacts, which itself fluctuates for many reasons. Linking a specific geological event to a specific stellar close approach requires trajectory calculations that become increasingly uncertain the further back in time you go. But the mechanism is real. The physics is established. Stellar close approaches perturb the Oort Cloud. Oort Cloud perturbations send comets inward. Some of those comets hit things. Scholz's star passed 70,000 years ago. Its perturbations are still propagating. Some fraction of the objects it disturbed will arrive in the inner solar system over the next several million years. We do not know which objects, we do not know how many, we do not know if any of them will cross Earth's orbital path in the wrong moment. There is something specific about this story that separates it from the others in this category. Gliese 710 is coming. We know it. We have calculated it. We have a date. Its arrival is in the future, and we have 1.3 million years to contemplate it. Scholz's star already came. It is already done. The event that planetary scientists classify as the most significant confirmed stellar close approach in the observable history of our solar system happened while human beings were already here, already looking up,
already crossing continents and oceans and ice fields with nothing but fire and bone tools and the cognitive architecture that would eventually produce radio telescopes and orbital mechanics. They did not know. They could not have known. A star passed within 0.82 light-years of the Sun, reached through the outer edge of the solar system, disturbed 1 trillion objects that had been undisturbed for billions of years, and departed into the darkness, all without producing a single signal that a human nervous system could detect, any light bright enough to name, any effect felt on the timescale of a human life or a human civilization. The most significant astronomical event in the recent history of our solar system was invisible to the species that lived through it. We are better now. We have Gaia. We have precise velocity measurements for 1 billion stars. We have the computational tools to run trajectories forward and backward in time with uncertainties that are narrow enough to be useful. We found Scholz's star's close approach because we built the instruments to find it and the mathematics to extract it from data. But we are better in the way that someone with a flashlight is better than someone in total darkness. The flashlight illuminates something. It does not illuminate everything. The stars we cannot measure, the dim ones, the fast-moving ones, the brown dwarfs that barely register in our catalogs, are still out there, still moving, still following trajectories we have not calculated. The next Scholz's star, whatever it is, wherever it is, may already be closer than 20 light-years. We may not know. 70,000 years ago, a small group of modern humans, perhaps a few thousand individuals, perhaps fewer, the genetic evidence suggests our species came close to extinction around that time for reasons still debated, were crossing unfamiliar landscapes, navigating by a sky they understood through pattern and myth rather than physics. Above them, 0.82 light-years away, a dim red star and its dark companion were completing a transit through the outer edge of the solar system that had taken tens of thousands of years to approach and would take tens of thousands more to recede. In the Oort Cloud, objects that had been orbiting undisturbed since the solar system formed were receiving gravitational nudges that would redirect their trajectories, some toward the stars, some toward the sun. The humans below looked up and saw the same night sky they always saw. The star was there, too faint to name, too slow to follow across a single lifetime. By the time we built instruments sensitive enough to find it, it had been receding for 70,000 years. And the objects it sent inward are still falling toward us, silently, on trajectories that began before civilization, arriving on schedules that end long after it.